It gives you the option to either do by hand or the negative function by filing theoretical. The whole zeros are equal you agree with that? You try to use CD by hand? Yeah. It gives you the numerator and denominator. So you need the coefficients with the numerator and denominator. I think verify that we got it.
Okay, Dan, you want to make your announcement?
Yeah. So I've had some requests by people that maybe didn't do quite so well in the midterm to kind of meet with me. So I think maybe what I'll do is I might try to start adding like some sessions on, I'm thinking Monday and Friday for people who didn't do too well in the midterm, but I want to focus it on people that are really kind of having fundamental issues with the material and like don't really understand maybe what's going on, or if they see a question don't necessarily know how to do things or even start the question. So if you feel like you're in that group, send me an email, and you know this is all going to be kind of anonymous, and it's supposed to be kind of like a smaller session to go slowly and really explain kind of some of the material again, so that we can kind of get you guys to closer to where you can be. So send me an email and we'll get that all arranged.
Okay. All right. Couple of announcements. There's a homework due today. It's really a lab. Pick up the solutions on your way out. It's homework due next Friday off of Chapter 8. And really, that's about it. At the end of last Wednesday's class, I did a show of hand type thing about DFTs, and also I examined the notes from a fellow by the name of Carson. Carson, are you here? Yeah. Okay, great. So I did pick up your notes from Rosita. And I looked over the homeworks for Gaspar's class, which seems to be the main feeder to this class, and also the lecture notes. There doesn't seem to be a lot on DFT, but since there seems to be a larger audience today than there was on Wednesday, I'd like to spend like 3 more minutes of doing another show of hands, just so that I can go through DFT at an appropriate speed, depending upon. I mean, strictly speaking, if Gaspar covered DFT, I shouldn't be covering that. On the other hand, looking at the coverage that he did do, and also considering the fact that a sizable percentage of you have not seen DFT in your undergraduate courses if you came from a different class and didn't take 120, I would have to go through it. So the issue is, at what speed do I go through it? And that's determined by how many people have seen it before and to what depth. So let's just do a quick show of hand, repeat of last time's lecture. How many people have been formally taught DFT in any course in the past? It's like a left half plane versus right half plane. Okay. And how many people, for example, have been taught about discrete Fourier series? Okay. How many people have heard of the word periodic convolution? Okay, and how many people have heard of the word circular convolution? Raise your hands this time really high up, because there seems to be fewer. Okay. And how many people know the relationship between circular convolution and linear convolution? Okay, and you two, you were not undergrads here. How many people know how to use DFT to do linear convolution? How many people know how to use DFT to do circular convolution? How many people know how to use DFT to do periodic convolution? Okay, I think I get an understanding. And one last set of issues. How many people know what decimation in time FFT is? How many people know what FFT is? You know what FFT is, but you don't know what? You all know what FFT is, but you don't know what decimation in time FFT is. So what do you know about FFT? It's Fourier transform, but faster. That's a good one. So when I cover FFT, I'll be really fast. So fast, you can't even copy. Not that I was slow already. Slow now. How many people have heard of the term decimation in frequency? How many have heard of the term butterfly as it relates to FFT? Okay. And let's see, what other buzzword can I throw out here? Okay. How many people know what in-place computation is? Yeah. Okay, actually there's like one person, this fellow here, who knows everything. I'm gonna take. And you're taking this one anyway. Yeah. And this is really the best, right? Of all the no comparison. Okay, so you know just about everything. But can I ask you, when you do the course evaluation at the end, don't say that it was a repeat of what I saw before, because you already took 4 courses before. Okay, all right, I think I get an understanding. So I think most of you know a little bit about what DFT is, but not all of you. Most of you know what circular and periodic convolution is, but you don't know how to use DFT to do it. So, okay, let's get going then. So let me start by talking about discrete Fourier series, and let's just do that. And we'll make the discussion on discrete Fourier series very short, because the only reason I want to talk about it is because when we get to properties of DFT, it's much easier to deduce properties of DFT if you know what the properties of discrete Fourier series are. So, if you will, I'm going to introduce a tiny little transform called discrete Fourier series, but the only purpose of it is to help us understand DFT a little bit better. So, let me start with discrete Fourier. Actually, I'm going to bring the thing a little bit. Thank you. Discrete Fourier series. So, why throw another transform at you? So let's go over all the transforms we know so far. We have a transform that takes a continuous time signal x of t and gives us x of omega, which is the continuous time Fourier transform, right? And t is continuous and omega is real and continuous, and it's just x of t e to the minus j omega t dt, going from minus infinity to plus infinity. That's continuous time Fourier transform. Then we started off this class with a different one. We start with discrete time signal. That means this n is an integer. Here this one was real, this one was real, here this one is integer. We did DTFT, which is the first topic we covered in this course, which I'm sure you'd seen in 120. And it resulted in x of omega, where omega again is real, and it was a summation over n, x of n, e to the minus j omega n. Then we generalized that to z transform. So z transform, again, you start with x of n, which is a discrete time sequence. And after you do the z transform, you get x of z, which is the summation over n, x of n, z to the minus n. Let's see. Any other transforms we talked about in this class? Not really, not yet. So what I'm going to talk about today, and next time's lecture, just to give you a bit of a preview, I'm going to start with what's called discrete Fourier series. And what it does, it starts with a periodic sequence. So this is integer still, but this is a periodic sequence. And gives me another periodic sequence, x tilde of k, which is summation over n, x of n, e to the minus j, 2 pi n k over n. And so that's what we're going to be talking about today primarily. And then we'll move on to yet another sequence, x of n, where again n is integer, but this thing is not periodic, but it's finite length. Okay, so here this is discrete time signal, but it could be infinite or finite length. For example, you could compute the z transform or the Fourier transform of an infinitely long sequence. H of n equals a to the n times u of n. That's an infinitely long sequence. We can talk perfectly okay to talk about its Fourier transform, discrete time Fourier transform, its z transform. Here the same. It could be infinitely long or finite long. But when I talk to DFT, discrete Fourier transform, I'm dealing with finite length sequences, and so there's only really like n numbers here, and then the transform of it I denote by x of k is the summation x of n e to the minus j 2 pi n k over n, and this is really from 0 to n minus 1 because I'm assuming this is finite. So I start with a finite length thing, and I end up with a thing that's integer here. It's x of k. K is integer, and this is a finite length. Okay, so right off, these are the two things we're going to cover. But right off the bat, you can immediately see what the advantage of DFT is. Again, the reason I introduced not many sequences in real life are periodic. We don't really care too much about periodic signals. The only reason I introduced that is so that I can get to this. But now, the reason this is an important sequence is several-fold. Of all these transforms, it's the only one where in the frequency domain I can actually talk about an array of numbers, x of k, where this guy, the function, the variable here, is discrete. It's an integer thing. K takes on the value 0, 1, 2, 3, 4, 5. Whereas this is real, and z here is what? It's complex even. It's not only not discrete, but it has two variables. Here, x of k k is an integer, and you can deal with now in the Fourier, for the first time in your life in the Fourier domain, you can deal with something with an array of numbers that's discrete. So that's why DFT is important. And in real life computations and applications, when you program in computers, it's a lot. What you deal with is discrete time sequences, finite length arrays. An array goes in, an array comes out. So from a computational point of view and from an application point of view, almost 99.999999% of the time, this is what you'll end up dealing with. So in some sense, it's a lot more important than all of the other ones. But don't worry about having too many transforms. This thing is the same way as we know that these two guys are related to each other, right? If I start with a continuous time signal and I sample it and I get a discrete time signal, then its Fourier transform in discrete domain is related to its continuous time Fourier transform. And how is that relationship? It's that big summation, replicate, that we've already come across it 3 times. So these two are related to each other. These two are related to each other. X of omega is x of z evaluated on the unit circle. So these two are related to each other. And this guy is no exception. It's related to this guy, and it's related to this guy. And we'll talk about that. So in some sense, you can arrive at the DFT from 2 different perspectives. You can either arrive at it from discrete Fourier series perspective, or you can arrive at it from a discrete time Fourier transform. Just a bit of a preview. What you'll see in today's lecture and perhaps Wednesday's lecture is that equally spaced samples of x of omega are x of k. DFT is nothing but equally spaced samples of x of omega, or it's just one period of discrete Fourier series. I'll explain all of these in a little bit more detail momentarily. Okay. So this sort of a one-page thing explains everything sort of in one shot, if you will, and explains why we worry about DFT. Okay. So before I even get talking about DFT, I want to talk about discrete Fourier series, and I'll talk about 2 of its properties that knowing those would enable us to arrive at the desirable properties of DFT. Okay. So what is DFS, or what's discrete Fourier series, and how does it work? Well, it deals with periodic signals, which is periodic discrete time signals, if you will. Okay, and what do I mean by periodic? I mean x of n is equal to x tilde of n, and whenever I put this little tilde up there, I'm denoting something periodic. So let's just keep that notation between us. X of n is equal to x of n plus k times n, where n is any integer, and it's the period. Okay. Just mind you, there's another thing, continuous Fourier series, that you also talked about, and that's also similar to this thing. It deals with periodic continuous time signals, but for now we don't talk about that. So what's the idea behind discrete Fourier series? The basic idea is to just decompose x tilde of n in terms of exponentials, and that are periodic with period n. Because x tilde of n is assumed to be a periodic signal with period n, then it makes sense to decompose it along exponentials that are also of period n. So how many exponentials of period n are there? How many discrete time exponentials of period n are they? N. And what are those? They're denoted by this. E sub k of n is e to the power of j 2 pi nk over n, where k ranges from 0 all the way to n minus 1. So that means there are n periodic exponentials with period n. And what I'm saying when I say decompose it, what I really mean is write down x of n as some sort of a linear combination, k from 0 to n minus 1, of these exponentials, e to the j 2 pi nk over n. And here is some function of k. It could be alpha of k, beta of k, but let me just call it x of k. Okay? So it's a little bit weight times exponential with k equals 0. Capital X of 1, that's the weight corresponding to exponential with e to the j 2 pi n over n. X of 2, e to the j 2 pi 2n over n. X of 3, e to the j 2 pi 3n over n. 3 little n over big N. So these are all functions of n. If I were to draw as a function of n, the real part of e sub k of n, they'll all be some functions, sinusoids going up and down, etc. Right? So if I weigh each of those sinusoids of different frequencies with the proper weight, add them up together, I can describe any periodic endpoint sequence. That's what this thing is telling me. And these guys are periodic with period n. Let me just prove to you. So let me just show you. So this guy e sub k of n is periodic with period n. And what do I mean by that? What I mean is e sub k of n is equal to e sub k plus Rn of n. Okay, where R is just some arbitrary integer. So let's prove that. It's pretty straightforward. Well, e to the j 2 pi nk over n, is it equal to question mark e to the j 2 pi k plus Rn over n? And the answer is yes, because you separate this exponential out, and what you get is e to the j 2 pi k over n Here? That's correct. Is j 2 pi. Thank you. So e to the j 2 pi kn over n times e to the j 2 pi n Rn over n, and the n's cancel out, and this is just 1, so this is e to the j 2 pi kn over n, which then indeed is equal to left-hand side is equal to the right-hand side. So these are periodic, no question about it. So in other words, what does that mean? It means e sub 0 of n is equal to e sub capital N of n is equal to e sub capital 2n of n is equal to e capital 3n of n, etc., etc. And then e1 of n is equal to e n plus 1 of n is equal to e 2n plus 1 of n, da 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 da, etc. Okay? So the question is, so we have these exponential functions, e sub k of n. They're discrete time and they're periodic with period n. Okay? And what discrete Fourier series is essentially doing is decomposing my signal x tilde of n along these exponentials. This is the weight of my decomposition for the kth exponential. And I can let k range all the way from 0 to n minus 1, and I get different weights for this particular exponential. So I'm just saying the right mixture of this exponential creates x tilde of n. That's all I'm saying. The linear weighted sum of these exponential can result in any periodic sequence of period n. That's really all that's happening. And where was another context in your life that you saw a right linear weight of two things resulted in an arbitrary thing?
Taylor series?
Yeah, in what sense?
You have an arbitrary of polynomial. Terms of polynomial.
That's sort of more of a series conversion type thing. Let's in linear algebra, right? If I have a two-dimensional suppose I'm sticking to 2 dimensions, x and y, and I have an arbitrary vector, and I can decompose that in terms of linear weight of 2 unit vectors. This is 1, 0 vector, and this is 0, 1 vector, right? So I can say, you know, any arbitrary vector v, for example, is alpha times, this called is u0, and this called is u1, is some alpha times u0 plus beta times u1. That's sort of a decomposition of an arbitrary 2-dimensional vector along the basis functions, right? These are called the basis functions. You've already seen that in linear algebra. And where else have you seen it? You've seen it right here. Okay? I am writing down x of omega as linear sum of these exponentials, the weighted linear sum of these exponentials. You've seen it, and here in continuous time Fourier transform, before you even took this course, here I don't have a discrete summation, instead I have an integral, which is more or less the same thing, right? So what I'm saying is x of omega is a linear weighted sum of these exponentials. And how much does it weigh? Well, for an exponential at time t, the weight is x of t. So you've seen it over and over. You saw it with continuous Fourier series as well. Linear weighted sum of periodic continuous time exponentials, or cosines and sines, results in an arbitrary periodic function. So if you have all linear weighted sum of cosines and sines with period t, results in building an arbitrary continuous time periodic function of period t. Okay? Or you can make this analogy in 3D. You can make it in 4D. It's a basic idea. It's called decomposing something into its constituents. So these are the constituents for the 2-dimensional vector case. So in this example here, our constituents are these exponentials. Because we're dealing with periodic signal of period n, there's n distinct exponentials at period n, and I'm decomposing that along those n functions. So it's a little bit times exponential number 1, a little bit plus another weight factor times exponential number 2, another weight factor times exponential number 3. Add them up and you get that. Okay? Is that concept clear? Okay. So the question that I'm going to ask now is, these are sort of the weights, if you will. How do I compute these weights? All right. How do I know how much of the first exponential, how much of the second exponential, how much of the third, fourth, fifth, seventh, eighth, and all the way to n? How much of them do I add up to get my x of n? Right? The same thing here. You know, this is the one-way thing, and then there's the reverse way of it. So how do I figure out how much to do that? And the answer is, I'll give you a proposal, and then I prove to you that's true. So question is how to find the weights, which are really just x of k. Well, here's my proposal. I can just say, I propose that x of k, which is those weights, can be computed, and how do you think we're going to compute x of k? Based on what? What signal do we use to compute x of k? Yeah, we're going to use x tilde of n, because depending if we have different signals here, we get different weights. So how we compute the weights is highly dependent upon what signal it is we're decomposing. These are the weights for that signal, right? Every signal has its own set of weights. So it's sort of like their fingerprints, just like every one of us have our own fingerprints. I am made of these 10 fingerprints. That uniquely specifies who I am. The same with you. And there's other identifying things like your iris or whatever. But this signal, these are its weights. These are its fingerprints, if you will. So my proposal is x of k is the summation from n equals 0 to n minus 1, x tilde of n, e to the minus j, 2 pi nk over n. And how funny, if I put these things together, you can see that the forward relations and the backward relations are sort of symmetric. They're almost identical. I've just replaced the plus j here with minus j, and that's it. But that is my proposal, and you shouldn't really take it at face value, you should ask me, is that really true? Does that really work? Yeah. And the proof of it is very, very simple. Plug this x of k into this, could you zoom up just a little bit? Plug this proposal that I have for x of k into this and see if you get x tilde of n back. So that's, so how do I, or vice versa. It doesn't make any difference. So replace the x tilde of n from this equation, from here, into this, and see if you can show that the right-hand side is equal to the left-hand side. So x of k, question mark, is equal to summation from n equals 0, n minus 1. And now I'm going to replace this with this whole blah here. And what's that blah? Was 1 over n summation k equals 0, n minus 1, x of k, e to the j, 2 pi nk over n. And by the way, to make myself not so miserable, because I already have k, I'm going to change this dummy variable to l. L, x of l, e to the j, 2 pi l, 2 pi n. So that is the expression I have for x of n. And now, so I just replaced x of n with the front thing in the parentheses, and here's the exponential, e to the minus j, 2 pi nk over n. That's just repeating itself here. And every time you have summations like that, the easiest thing to do is reverse the order of summations. So it's still question mark, I bring the L summation out and the N summation in. So summation from L equals 0 to N minus 1 of capital X of L of 1 over N. And now I'm going to bring the N summation in, N equals 0 to capital N minus 1. And I'm going to lump both of the exponentials together. E to the j, 2 pi L minus k little n over n. Okay? Now, what's this quantity here? Does anyone know this quantity by inspection? It's some sort of... What happens if L is equal to K? It becomes 1, or L is, or even L is a multiple integer of K. Then this whole thing, this exponential becomes 1. I add up 1 n times, I get n over n is 1. So it seems like sometimes this thing is 1. And what happens some other times where L is not a multiple integer of K, or vice versa? It ends up being sum of a bunch of exponentials and it ends up being 0. So to prove that, let me call this quantity A. So what is A? Well, let's just do 2 cases. Case 1. If L minus K is an integer multiple of n, in other words, L minus K is R times n, then A becomes 1 over n summation of n equals 0 to n minus 1 of e to the j 2 pi, and now I'm going to replace L minus K here with Rn. Rn, n over n. So these n's cancel out, and I get e to the j 2 pi Rn. R is an integer, n is an integer, e to the j 2 pi, any integer is just 1. Add up 1s a whole bunch of time, you get n over n, and that's 1. Finished. In case 2, with L minus K is not equal to Rn, that means L minus K is not an integer multiple of n. Then what happens? Then this guy A is 1 over n summation for n equals 0 to n minus 1 of e to the j 2 pi L minus K n over n. And that's a geometric series, and to do a geometric series you have a formula that does it. In particular, I want you to recall that if I have summation n equals 0 to n minus 1 of alpha n, it's 1 minus alpha to the capital N over 1 minus alpha. So if I plug that into this, what I get is that A is equal to 1 over n. Replace alpha with that exponential here. 1 minus e to the j 2 pi L minus k n over n. 1 minus e to the j 2 pi L minus k over n. And now this n here cancels this n, and the numerator and hold on a second. Yeah. And so the numerator becomes e to the j 2 pi L minus k. L and k are integers. L minus k is an integer. E to the j 2 pi an integer is just 1. 1 minus 1 is 0. The whole thing becomes 0. You might say, why didn't you apply this geometric series idea here? What would have failed? The problem is what? If L minus k was a multiple of n, not only would the numerator be 0, the denominator would have been 0, you would have had 0 over 0, you would have had undefined, and that would have gotten you into trouble. That's why I separated into two cases. Okay, question?
It doesn't make a difference. I think you're missing a little n.
Here, now?
Yeah.
Okay, I always drop these n's.
Oh,
No, I am not missing an n. That gets summed out in the summation. Absolutely. That's the, yeah, that's the geometric ratio. It doesn't have any ends. Okay? So the reason I separate these two cases is because, as I said earlier, if L minus k is a multiple of n, both of them become 0 and you're in trouble. So what can we conclude from here? What is A? Sometimes it's 0, sometimes it's 1. So the easiest thing is to say A, and what's the easiest way of describing a function that's sometimes 0 and sometimes is 1? It's a delta function. It's delta of L minus k minus Rn. When L minus k is equal to Rn, this becomes 1. When L minus k is not equal to 0, is not equal to Rn, this thing is 0. So A is this delta function. So come back here, and A is nothing but delta of L minus k minus Rn. And so coming back here, this is equal to what then? It's the summation from L equals 0 to n minus 1 of x of L, delta of L minus k minus Rn, and now we can apply the sift property. You're summing over something times a delta, and that thing is going to take on the value of it at delta. So it's going to become x of k plus Rn, where R is any arbitrary integer. This is arbitrary integer. In particular, hold on a second. In particular, it's true for R equals 0. So this is equal to, I can write this as it's equal to x of k. It's equal to x of k plus n. It's equal to x of k plus 2n, x of k plus 3n, x of k minus n, etc., etc. So I'm done with this. This is no longer a question mark. I'm done with showing x of k is equal to x of k. Furthermore, I showed that this x of k is a periodic sequence. Okay, now there's a question.
Isn't A a delta train, or is it just a delta function?
It's a delta function, and it's equal to, it's a delta function that takes on the value 1 for any arbitrary R. Right? Because this is any arbitrary R. When L minus k is any, this R is an arbitrary number. It's any arbitrary integer. So here, R is any arbitrary integer. So when I write it's x of k plus Rn, again, R is any arbitrary integer. Because R is any arbitrary integer, it's equal to x of k plus n, x of k plus 2n, etc., etc. So not only did I show x of k is equal to x of k, not only was my proposal good, I also showed at the same time that x of k is periodic. Is that clear? Okay. So from this discussion up here, if you can zoom up just a tiny bit, the conclusion that we end up getting, let me write it down here, is that x of k is equal to x of k plus Rn, where R is an arbitrary integer. And therefore, what that means is not only did this proposal was true, I'm just proving that x of k is a periodic sequence. And what period does it have? It has period n because it satisfies this relationship. It has period n. So from now on, I'm going to refer to x of k as because it's a periodic sequence. I'll put a tilde on top of it. It's x tilde of k. Okay, so that's good. So coming back where we left here, so my proposal here was x of k is this, and remember, so these weights that I was talking about, the sequence of weights that I was talking about, is indeed given by this equation, right? This is what we proved. The left-hand side equals right-hand side and all that. And so if I were to combine these, so I'm essentially done. This is a forward discrete Fourier. This is a forward discrete Fourier series, or in other words, the analysis part, and this is the reverse discrete Fourier series. In other words, the synthesis part. And I can write both of those two things down. So from these two things, what I can conclude is the Fourier series pair. The analysis part is just x tilde of k, and remember we just showed x of k is periodic, so I'm just going to write x tilde of k is summation from n equals 0 to n minus 1 x tilde of n e to the minus j 2 pi n k over n, and the synthesis part is just, in other words, synthesizing the signal back, x tilde of n is summation from n equals 0 to n minus 1 of x, capital X tilde of k. This is the weights. This is the coefficients. E to the plus j 2 pi n k over n. So you start with a periodic endpoint sequence. You get a periodic endpoint sequence. And then you get the periodic endpoint sequence, and you get another periodic endpoint sequence. I know I sound silly, but that's all there is to it. So DFS, to make a long story short, it maps a periodic endpoint, or it transforms a periodic endpoint sequence in time domain, x tilde of n, back into another periodic endpoint sequence in frequency domain. And that's x tilde of k.
The synthesis equation has the wrong summation variable.
Ah, thank you. This should be k. Yes, and there's 1 over n missing too. Thank you. So this is it. This is it in a nutshell. Now, before I move on talking about properties, let me just bite the bullet and show you like one example of this thing. So the example is what? Again, zoom up if you can. So suppose that I give you this periodic sequence x of n, which is summation r minus infinity to plus infinity delta of n plus rn. That's a train of delta functions. Okay, it takes on the value 1 here, here, so it's a periodic sequence with period n. And if I plug it into, and what do you think is the discrete Fourier series of this thing? Well, the discrete Fourier series is x tilde of k is equal to summation from n equals 0 to n minus 1 of, plug that in, r minus infinity to plus infinity delta of n plus rn e to the minus j 2 pi n k over n. And what do you think the answer is by inspection? It's just 1. You bring the summation on, and the delta is, you apply the SIFT property, and what you get is just 1. And how does this thing look like? It's a periodic sequence of period n, so it has 0 all the way to n minus 1, but it happens to be 1, 1, 1, 1, 1, 1, 1. And then at time n, another, so this is one period, that's another period, but it's 1, 1, 1, 1, 1, 1, 1. And is that surprising? No, it's a train of delta function, train of delta function. You have a 1 here, and you have a bunch of 1s here. Okay? So, and you can also, and another, this is n minus 1, I'm sorry, minus n. Minus 1, so it's another 1, 1, 1, 1, 1, 1, 1. So you can also do the reverse of this thing. So you can also plug in the synthesis pair now, okay, this equation, and say that x of n, x tilde of n, is 1 over n of summation k equals 0 to n minus 1, and now x tilde of k is just 1, so 1, e to the j 2 pi n k over n. Okay? And that is equal to, because of the forward Fourier transform, that's equal to summation r from minus infinity to plus infinity delta of n plus rn. That is what our x of n is. So that's actually an identity. Let's remove this 1 because it doesn't do anything. So that is an identity that we're going to use over and over, which is the sum of the exponentials is just a train of delta functions. It's essentially the same thing we talked about earlier. But I'm going to refer to this in future lecture. I'm going to call this equation dot train. Okay. All right. So let's move on to the shift property now. Let's prove some of the basic properties of discrete Fourier series, and these are very, very simple. So I won't go over deriving them, but I think it's important to just state them because in 10 minutes or in next time's lecture we're going to use them. So if x of tilde of n, which is a periodic sequence in time domain with period n, has x tilde of k as its discrete Fourier series, how about x tilde of n minus n naught? It's going to be an exponential, e to the minus j 2 pi n naught k over n times x tilde of k. Shifting corresponds to multiplication by an exponential. The proof follows just like all the other proofs we've done, so I won't go over it. Maybe, Dan, this is something you want to show in the recitation. Next, I move on to periodic convolution, which some of you said you've already seen, but let's just go over it real quickly. And what that means is, if I have a periodic sequence x tilde, and I denote it by this convolution with a circle around it, and I convolve it periodically with x2, and this is a period n, and this is with period n, and this is periodic convolution, it's called. I get a new signal that's periodic. I call it x3 of n, and that is also of period n. And by definition, periodic convolution of these two things looks very much like the old convolution you know. This is period n, this is period n, this is period n, so it's a summation from m equals 0 to n minus 1 of x1 of m times x2 of n minus m. And the property that I want to show is that if in the time domain I do this kind of periodic convolution, then x3 of k is equal to x1 of k times x2 of k. So the discrete Fourier series of this new signal, which is the periodic convolution of these two, is the product of these two discrete Fourier series. Just so that you can imagine intuitively how periodic convolution works. How does it work? it's the same thing as before. You have one long periodic sequence, you have another one periodic sequence, you flip one, you drag one, and you multiply and add. But another easier way to intuitively think about it is think of a cylinder sticking out. And think of my 5 fingers as being the 5-point sequence, let's say x1 of n. Each one has a value, 1, 5, 9, 30, 45, or something like that. And think of x2 of n, another, my other 5 fingers, and each one has its own value, 35, 29, whatever. And for each different value of m, you multiply these by that and add. And then you shift it, and then multiply and add. But when you shift, because the thing is periodic, it's as if you go around the perimeter of a cylinder. You might want to put the camera on me now for people on the web who are watching it. Yeah? Okay. And then I change m by 1 more, and it just rotates. Man, okay. I should have been a monkey. Okay, it just rotates. So then, as I do, it's like a machine, right? My shoulder doesn't let me go all the way, but so you get the picture how this works. It's as if these points are along a cylinder, and there's 5 points because this is a 5-point sequence, and that's the other x1 and x2 are each 5-point sequences. There's only 5 clicks to the cylinder. Click, do. After I get to the 6th position, it's the same as what I had before. That's why x3 is also a periodic sequence with period 5. And x7 is the same as x2. There's only 5 positions, if you will, in this game. Is that clear? Okay. So this is really all I want to talk about as far as discrete Fourier series is concerned, and I want to now switch gears and talk about discrete Fourier transform. As I mentioned at the very, very beginning of the class, it's a good transform because it starts with a finite length discrete time sequence, and it gives me a finite length discrete space discrete index sequence. So it's really fantastic. So what DFT does, which is discrete Fourier transform, it starts with x of n, and it gives me x of k. So this is an n-point sequence, and this is another n-point sequence. So you can think of DFT as sort of a box. N points go in, n points go out. And that's what's so good about this. None of our other transforms here ever had a discrete index. They all had either complex or real, so they were non-computable. Okay? So there's 2 ways of arriving at DFT, as I mentioned earlier. One is to relate it to discrete Fourier series, and since we just did discrete Fourier series and it's fresh in your mind, let me start with that. And another way is to arrive at it from discrete time Fourier transform. So discrete Fourier series is related to 2 things. I'm sorry, discrete Fourier transform is related. It can be related to discrete Fourier series or discrete time Fourier transform. So let me start by talking about this. So here we go. The first approach to DFT is via DFS, discrete Fourier series. And the way it works is as follows. You start with a finite extent sequence, x of n. That's what this is all about. Discrete Fourier transform doesn't deal with periodic infinite length sequences. It deals with a finite extent n-point sequence. Okay? So start with a finite extent sequence, x of n, which is n points long, and it goes from little n equals 0 all the way to n minus 1. And if I want to exploit discrete Fourier series, and discrete Fourier series deals with periodic signals, I better periodicize x of n. So even though this is not really a word in the English language, but let's just use it anyway, periodicize x of n to get the periodic version of this guy, x tilde of n, with period n. Why period n? Because this was an n-point sequence. Okay? So then essentially x of n is just one period of x tilde of n. It's x tilde of n times this function which I call r sub n of n, and what this guy does is extracts one period of x tilde of n. And how does it, what's the definition of it? Well, r sub n of n is equal to 1 when n is equal to 0 all the way n minus 1, and is equal to 0 otherwise. That's how it extracts one period of this guy. It just keeps the first endpoints and throws away everything else. Okay? So I start with my x of n, I make it periodic, that means replicated, right? So what's this thing, what does this periodization do? In other words, what's x of n? Well, x tilde of n is summation over n, x of summation over r, x of n plus rn. R goes from minus infinity to plus infinity. That's what the periodization does. It just makes this thing replicated, right? But so to start from x of n to go to x tilde of n, I plug it into this relationship. Now that I have x tilde of n, I want to get x of n, I multiply by this r guy, and I get just one period. Is that clear? There's a bunch of words for almost nothing. It is. There's not much to it. And a lot of symbols. And step number 3, now that I have a periodic signal, what do? I take its discrete Fourier series. Remember, what was the purpose of this whole exercise is to relate DFT and DFS, okay? So step number 3, take discrete Fourier series of x tilde of n. We couldn't have taken discrete Fourier series of x because x wasn't periodic, but first we made it periodic, now we take discrete Fourier series, and that gives us discrete Fourier series coefficients, x tilde of k, okay? And then we take one period of this skin. Remember, what we want to end up with is DFT, and DFT, the final answer here is not periodic, it's just n point. So what's the simplest way to get from a periodic thing, which is period n, to an n-point sequence? Just extract one period. Very easy. So take one period of x tilde of k to get x of k, which is just the DFT of x of n. So in other words, x of k, how do I make it to be one period of that? Well, it's x tilde of k times the one period function is again r sub n of k. Because this is n, that means take the first n points of it and throw away everything else, and boom, that's the DFT. So start with x of n to summarize everything. Make it periodic to x tilde of n. So this is an n-point sequence. This is periodic with n point. And then take the DFS, and that gives you x tilde of k. That's also periodic, but this time in frequency domain, n point. And then extract one period, and you get x of k. And that's n point also. Okay? That's really it. That's the relationship between DFS and DFT. So pictorially, if you will, what's happening is as follows. I start with x of n. Let's say it was 0, 1, 2, 3. That's my 4-point finite length sequence. I make it periodic. And how would I make it periodic? 0, 1, 2, 3. 1, 0, 1, 2, 3. 0, 1, 2, 3. 0, 1, 2, 3, etc. So I make it periodic. That's x tilde of n. And then I compute x tilde of k. So it'll look some periodic thing again. And then I extract one period of it, which is just this guy. That's it. 0 to n minus 1. That's it. That's the DFT of that. So make this periodic, take DFS, and then extract one period. So based on all of what I just said, based on this relationship I just said, what is the definition of x of k? What is the definition of DFT? Well, it's just one period of x tilde of k. So based on all of that, the definition of DFT is as follows. X of k, which is the endpoint DFT of x of n, is equal to, it's equal to something for k in between, k in between 0 and n, and is equal to 0 otherwise. And that thing is just summation from n equals 0 to n minus 1 of x of n e to the minus j 2 pi nk over n. It's the same expression as we had before for discrete Fourier series, but because I'm only extracting one period, that's only true for k. These guys are k's. This is only true for k between 0 and n. Not for all these other k's, because I'm not keeping these guys. I'm just keeping one x, and it's 0 for all other values of k. That's it. And x of n, on the other hand, is given by the same thing. The same way as we would have gotten x tilde of n, but we only want one period of it. So it's 1 over n summation k equals 0, n minus 1, x of k e to the j 2 pi nk over n, but only for n in between n and 0, but it's 0 otherwise. Okay? So now, I'm done with my first thing, which was relating DFT to DFS. And in the process, I came up with a formal definition. Now I want to relate DFT to discrete time Fourier transform. I want to relate DFT to x of omega, discrete time Fourier transform. And how are those two things related to each other? So now relate DFT to DTFT. Well, that's the definition for DFT, and let's write down the definition for DTFT. X of omega is summation over n from 0 to, if I have an n-point sequence, it's 0 to n minus 1 of x of n e to the minus j omega n. So stare at this thing up here and stare at this thing down here. How is x of k related to x of omega? Compare this guy and that guy, this guy and that guy. How are they related to each other? That's right. They both have summation n equals 0 to n minus 1. They both have x of n. They both have e. They both have minus j n. But the only thing is omega is replaced with 2 pi k over n. So then x of k is equal to, well, it's 0 otherwise. Let's not forget that. But for k in between n and 0, it's just x of omega evaluated at omega equals 2 pi k over n. Because all I have to do is replace omega with 2 pi k over n, and I get, can you zoom by? I get smack this relationship here. This omega, I replace it with 2 pi k over n, boom, I get it. Can you zoom down actually so that, yeah, I want, hold on, that I want this and this to be, yeah. Okay? So, and a lot of you have seen this, right? Or at least half of you, this left half have seen it. The right half hopefully is still clear, right? So what can I say in words? What can I say about DFT? DFT is equally spaced samples of DTFT. So DFT is equally spaced samples of DTFT. That's all there is to it. And pictorially what's happening, let's look at some x of omegas. So pictorially what's happening is this. If x of omega, first of all, remember x of omega was, as a function of omega, was a periodic signal, right? It looks like this. It's a periodic function, not signal. And with period 2 pi, right? It goes minus pi, plus 3 pi, etc., minus 3 pi. And so if I have if I'm talking about the 4-point sequence and I have a 4-point DFT, what are those? I'm sorry, 8-point, let's say. What are those 8 equally spaced points? It's omega equals 2 pi k over 8, where k ranges from 0, 1, 2, 3, 4, 5, 6, 7. So when k is equal to 0, I get omega equals 0. So that is it. I'm sampling. That's my first sample. When k equals 1, I get 2 pi over 8, which is pi over 4. That's another sample. K equals 2, I get 2 times pi over 4. That's pi over 2. K equals 3, I get 3 times pi over 4. That's this point. And k equals 4, I get 4 times 2 pi, 8 pi over 8, we get pi. So that's this point. So this is k equals 0, 1, 2, 3, 4. K equals 5, I guess 10 pi over 8, which is the same as this, but this thing is periodic with respect to the other. Well, let's just do it this way. K equals 5, I get this point. 6, I get this point. And 7, I get this point. And 8, there's no 8, because 8 would have resulted in the same as k equals 0. So 8 would have been the same point as that. And that's perfect, right? We only keep, so here's the 8 equally spaced samples of x of omega. They're pi over 4 apart. And these are my 8-point DFTs. And this is 0, and this is 2 pi. I stopped just before 2 pi. Is that clear? So why is this exciting? Because for the first time in our life, I know this is not really your first time. You already did some labs that showed you how to do this, but we don't have to deal with x of omega. This omega was a real variable, and it's very difficult to program up something that, coming up with arrays of real variables is very difficult. But now, an 8-point sequence comes out, an 8 number comes out. And that 8 numbers uniquely specifies my 8-point sequence. I can start from the time domain, go to frequency domain, go to time domain, back and forth. And I don't have to deal with any of those continuous variables, little omegas, big omegas, z's, none of that junk. It's all out the window. And one last thing before I end today's lecture, how about in the z domain? Just we've been throwing everything around here. So this is the z plane. Well, we already know. So this is real part of the z, and this is the imaginary part of the z. We already know that discrete time Fourier transform is the z transform evaluated on the unit circle. Good. It's like I always take, like, this is a birthday cake, and it's your kid's birthday. You take the knife, and every time I have my son's birthday, when I cut the knife, I always think about Z transform. And I do. I'd be lying to you if I didn't. But when I teach the course, I also remember that. So I tell it's a two-way street. So it's like a knife. I cut this cake, and the value of the cream on top as it traverses the value of that function. And for months you have to lose that weight after you eat that cake. But anyway, so that's the cake. You cut it and you get the DTFT. Now, samples of that cake. This is going to be distributed among the guests. This is for me. This is my son, my husband, my grandpa, friends. The samples of these guys. K equals 0, 1, 2.
So the candles represent the poles or 0?
Poles, I think. They have to be in the unit circle to have stability. So this is k equals 0. this is k equals 1. K equals 1 is pi over 4. K equals 2. K equals 3. K equals 4. 5, 6, 7. And thankfully, 8 falls right over k equals 0. Thank God. Everything works out okay. Everything is periodic. You go around. Okay? So these are the samples in the Z domain. If you can even think about sampling the Z transform at this point, and you get your DFT. Okay? So this is at pi. This angle is pi over 4. There's another pi over 4. It just goes equally spaced angles around. So these transforms that we're talking about are highly related to each other. Just to wrap up this lecture, just to give you a big picture of what happened today, we started with x of n, and it's an integer, and we already know what DTFT does to that. It gives us x of omega, where omega is a real thing. I'm really repeating what we had earlier. Then we start with x of n, where this is an integer, and aperiodic finite, I mean, it's a periodic finite, what am I saying? So, integer finite extent sequence, and I plug it into my DFT, and out comes x of k, where k is an integer, and this is related to that. And this is also related to DFS. And how is that? If I make this guy periodic, and out comes x tilde of k, then this is related to that, this is related to that, these are related to each other, and these are related to each other. These are both finite extent sequences. This is a periodic version of that. This is a periodic version of that. This is sample version of that. They're all related to each other. Okay? Okay, I think I'm going to stop now. You should be able to do the homework over the weekend. But if you come to Wednesday's lecture, you should definitely nail it. And what I'm going to talk about, don't forget to hand in your homework and pick up the solutions. Dan, do we have graded homeworks? We'll hand it on Wednesday. Okay. So next time what I'm going to talk about is the following. Is this. Yeah, well, it takes too long to explain, but we'll talk about the case where these guys are infinite extent. And we do some samplings of this domain. How do things relate to each other?